Okay, so this section is going to be isotopes and atomic mass. So let's start with isotopes. Isotopes are members of the same element that have different numbers of neutrons but the same number of protons. So below we have three different isotopes of silicon written out. We've got silicon 28, silicon 29, and silicon 30. We discussed before the mass number is written right behind. So silicon 28 has a mass number of 28. The atomic number we can determine from looking at the periodic table. Silicon is right here, Si, and it has the number 14. So the atomic number is going to be 14. As we discussed before, the atomic number is equal to the number of protons, and so the number of protons is going to be 14. Now the number of neutrons is going to be the mass number minus the number of protons. So this will be mass number minus protons. So we'll get 28 minus 14, and that will give us 14 neutrons. So let's see what numbers we get for the other two isotopes. The mass number for silicon 29 is going to be 29. The atomic number, well, it's the atomic number for silicon. It hasn't changed. It'll still be 14, and since it's a silicon atom, it'll still have 14 protons. So here we get 29 minus 14, and we get 15 neutrons. So that's the way that silicon 28 and 29 differ. It's the same number of protons, but different number of neutrons. So for silicon 30, we get a similar result. We have 30 minus 14. We have 16 neutrons in a silicon 30 atom. So let's look at this problem. Which pairs below are the isotopes of the same element? So just as a reminder, the mass number is the number up at the top. The atomic number is the number at the bottom. Okay, so this atom here has an atomic number of 8, and that makes it an oxygen. If I get you on the same screen here, it makes it an oxygen atom with a mass of 15. This atom here has an atomic number of 7. That makes it a nitrogen, and it has the same mass as the oxygen beside it. They both have a mass of 15, but they are different elements. One is nitrogen and one is oxygen, so that one is not an isotope of the same element. These two, they both have 6 in their atomic number spot, so they're both carbons. They have different masses, but that's okay. They can be isotopes and have different masses. This is a 7 in the atomic number spot, and so that's a nitrogen. This is an 8, and so it is an oxygen. So these are not isotopes. They are different elements. Okay, atomic mass or molar mass. This is a weighted average of all the naturally occurring isotopes of an element. It's found below the element symbol, and it's not going to be a whole number. So here's the example with copper. Here's the element symbol, Cu. Above it, we have the atomic number. That's how many protons are in a copper atom. Below, we've got this number. It has a decimal point. It's not a whole number. and it's a weighted average of all the different isotopes that are found in nature. Well, how is this number calculated? Copper is made up of two isotopes. It's a copper 63 with a mass of 62.9296 AMU with a relative abundance of 69.15. There's also another form of copper, copper 65, with a mass of 64.9278 AMU. Whenever I get a problem like this, where I've got lots of different numbers, I like to put them in a nice table so that I can keep them all straight and figure out what I'm doing. So let's do copper 63. Copper 63 has a mass of 62.9269 AMU. The relative abundance is 69.15%. Copper 65 has a mass of 64.9278 AMU. And they didn't give us the abundance, but we know that the total abundance must be 100. And so we can subtract and figure that there's 30.85%. I got this number by taking 100%, subtracting 69.15%. Because the total is going to be 100. Okay, the formula for doing a weighted average looks like this. Our atomic mass is going to be equal to the abundance of isotope 1 times the mass of isotope 1 plus the abundance of isotope 2 times the mass of isotope 2. I'm going to move this up just a little bit. There we go. So let's start with the pink. We've got an abundance of 0.6915. I moved the decimal place over twice because this is a percentage and I don't want to keep it as a percentage. So to lose that percentage sign, you move the decimal place. The mass is 62.9296. And then we'll be plus, we'll do the other one, abundance of 0.3085 times 64.9278. And I will get 43.516 here plus 20.030. That will equal 63.55. This will be an AMU. I dropped my signs, but this was mass was an AMU. Atomic mass unit. All right, and we'll see that that agrees with the mass that we find on the periodic table. Okay, so I've got another one, and I want you all to try it. Pull it up here. Try the chlorine atom, and then we will work it together. All right, so you've had a chance to turn off the video and turn it back on again. The mass of the chlorine 35 is 34 34.9689. These are all going to be AMU. And with a relative abundance of 75.76%. The chlorine 37 is 36.9695, and we can figure the percentage as 24.24%. These both need to add up to 100. So since we've got our table done, we can now just fill in our answers. The abundance of our first one is 75.7, it's 0.7576. The mass is 34.9689 plus relative abundance of 0.2424 times 36.9695. And that gives us an answer of 35.45, which agrees nicely with the periodic table.